Okay, just started recording. We did miss a little thing from the beginning. I was just saying that there are two documents over here they're found in the general documents folder here. Primer on proof and proofreading here that I want you to look over before Monday. All right, that's all I said. So let's go ahead and put away this for now and pull up our whiteboard. You can see what I was doing in calculus this morning. The good old days, limits and continuity. All right, so for today, we are going to begin with section 1.6, which is on called rules of inference. Okay, so rules of inference. This section will be on what's called an argument. We're going to learn about logical arguments. So an argument is a compound proposition of a certain form. It looks like P1 and P2 and ... and Pn, where the ... means, there's some number of P's here, P1, P2, P3, up to however many there are, some finite number of things. All of those conjoined together, conjunction, with and, all imply something called Q. So so this is an argument, right? It is essentially an implication, and on the left side in the hypothesis you have some sort of a conjunction. Possibly there could be a single, it could be like a single thing, just P1, but in general arguments usually have multiple things over here, and these things are called the premises. The premises, each one of those is a premise. They make up the hypothesis of this thing, and then over here you have the conclusion, right? Just like we call it for any old implication statement. This is called an argument, and an argument is valid if this yes, it always has to be and. Question in the chat. It always has to be and, not or. You don't want. Some of the statements, some of the individual premises could involve ors, but the premises all must be combined with and. Okay. An argument is valid. I think if this is a tautology, I just realized I forgot. I spent so much time preparing examples, I forgot to review the basic thing. I think it's if this is a tautology, but I got to check. Hang on. Oops. Yeah, I was right. Okay. If it is a tautology, right? Which means, remember, tautology means like that its truth value is always true. Okay. Otherwise, it's called an invalid argument. Okay. There's an alternative way to write, because arguments are sort of a special type of compound proposition. They have an alternative way to write them. So alternate format is sort of this vertical format, premise 1, premise 2, ... down to premise n, and then a horizontal line. And then we use this symbol that means therefore. This 3 dots means therefore. And that's where we put our conclusion. So it's like premise, 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 therefore conclusion. Okay, and that is the way I'll be writing arguments most of the time. Okay. So what we are going to be doing is 2 things. We are going to be practicing like looking at verbal arguments and representing them symbolically so that we can then use symbolic logic to analyze the argument and prove its validity. That's the two things we're going to be doing. We're going to be representing arguments symbolically and then proving their validity. Now, the question in the chat, what do I mean by is a tautology? Tautology means always true. So tautology means this is equivalent to T. There's no set of values for the variables involved that could possibly give you a false overall value. Okay. That's a tautology, is where the value's always true. Remember, P implies Q is only ever false when P is true and Q is false. So the idea is, if this is a tautology, it means that whenever all of these things are true, Q has to be true. There's never a situation where all the premises are true and Q is false. So that's what it means to be a valid argument. This is one place where you can have where like vacuous truth is really important, because if any one of these premises is false, if you have a false inside here, if any one of those premises is false, then the entire hypothesis is false, because it's and false. The entire thing is false. And then, but then the entire argument is vacuously true. So what that means is you can have a valid argument. It's a valid argument. It doesn't, its validity is sort of independent of whether or not the premises are true. Okay, let's look at a written example in order to understand that a little better. Okay. So for this first one, we're not going to use, this first one's going to be propositional logic only, no predicates and quantifiers. We'll get to predicates and quantifiers in just a minute. You can do arguments either just using propositions, or you can do them with predicates and quantifiers. So like kind of like this topic spans both the, basic propositional logic and the more advanced predicate logic. So let's look at this argument. This is an argument. Bob works part-time or full-time. If Bob doesn't play on the team, whatever the team is, right, baseball team or something, then he doesn't work part-time. If Bob plays on the team, then he is busy. Bob doesn't work full-time. Therefore, Bob is busy. So this is an argument. It has a bunch of premises and a conclusion. The idea here is that we want to prove that this is a valid argument by showing that if all the premises are true, then the conclusion has to be true as well. Okay? If any one of these premises is false, then the argument, the implication from that argument would be true vacuously, right? Just erase this here. I just realized I don't want to leave this in the notes here. Yeah, so if any one of those premises is false, then the argument is valid, or the argument could still be valid, not necessarily, but it could still be valid. Just because the implication would be satisfied by vacuous truth. That's the point I'm trying to make there. So really, we only have to consider the situation where all of the premises are true. Start by assuming all the premises are true. That's all we really care about when analyzing validity of an argument. Okay. this is something that is kind of important to keep in mind outside of math class as well. Like, this is something that's important to lawyers. Lawyers are interested in not only the facts, but also the validity of the arguments being made about those facts, right? So like you can analyze those two things. You can like consider those two things as independent of each other. There's the facts that are being used as the premises in a case, right? And those are either true or false, and you can, talk about whether those are true or false. But then there's also arguments being made based on those facts, and those arguments can be analyzed for validity independent of whether the facts themselves are true or false. And so an argument can break down if any of its premises are false, but it can also break down if it's not valid. And those are different things. Yeah. All right. So let's start by representing this argument with symbolic statements. So in order to do that, we first need to define some propositions here. So I'm getting my propositions. There's my propositions. So we're going to have P, F, T, and B. So P is Bob works part-time, and F is Bob works full-time. T is Bob plays on the team, and B is Bob is busy. Those are all the different things. Those are all the different statements being made here. So now I'm going to get back up here and I'm going to label these premises. 1, 2, 3, 4. 1, 2, 3, 4. Now I'm going to write symbolic versions of those premises over on the right side. So the first premise, Bob works part-time or full-time, can be represented as P or F using these prepositions down here. Okay. Then we have the second premise. If Bob doesn't play on the team, then he doesn't work part-time. So it's an if-then statement. It's an implication. And the hypothesis is Bob doesn't play on the team. So that would be like not T. The conclusion is then he doesn't work part-time. So not P. We have not T implies not P for that one. Moving on, 3, if Bob plays on the team. So if he does play on the team, T, then he is busy, then B. And 4, Bob doesn't work full-time. That's just a single statement of not F. So there are the 4 premises written symbolically. And then our conclusion, we can write, therefore, with our little 3-dot symbol, Bob is busy, which is just B. So we have our argument written verbally. We can translate that into a symbolic argument. This can be thought of, remember, this can be thought of as a one big implication statement like this, right? Premise and premise and premise and premise implies conclusion. And we want to show that that is a tautology, that it must always be true. Now, one way to do this is with a truth table, but that is sort of long, and I don't want to do it that way. Instead, we're going to practice a different strategy, which is to use what are called rules of inference. Inference. Okay. So if you have your reference sheet handy, go ahead and pull that up, because it has a bunch of rules of inference on the second page, or on the back, I guess, since I printed it double-sided. So here are our rules of inference. Now, what are these rules of inference? They are themselves arguments, but they're very simple arguments. So like the first rule of inference on here, which has this fancy Latin name, but all of these rules of inferences have fancy Latin names, or most of them. These ones aren't Latin. Not all of them are Latin. but some of them are. And this one's called modus ponens. And modus ponens is a very simple argument with two premises. One of the premises is P implies Q, and the other one is P. And if we assume P implies Q is true, and we assume that P is true, what we can do is conclude that Q is true. Okay, so that would look like this. It would look like P implies Q and P. All of that implies Q. That is a tautology. Or we could write it as P implies Q and P, therefore Q. Like this, right? It's basically like saying, hey, you have this valid implication, this true implication, P implies Q, and P, the hypothesis, is true, not false. So we're not in a vacuous truth case, right? We're in a case where the hypothesis is true. Then the only possibility to allow the implication to be true is that the conclusion is also true. Because otherwise, if the conclusion was false, you'd have true implies false, which is equal to false. So that would contradict the premise that P implies Q is true. Okay, so that's modus ponens. And then each one of these other rules of inference is another little argument, right? So like modus tollens is a similar one. P implies Q and not Q, therefore not P, which is kind of like an equivalent of modus ponens, but using the contrapositive equivalence. Hypothetical syllogism, if P implies Q and Q implies R, then we know that P in turn implies R. It's kind of like saying that there's this these implications sort of can be chained together. That's called transitivity. It's a transitive property. That word transitive is something we'll introduce a little more formally later in this semester. And you can look through the other ones, but most of them make a lot of sense. Most of them are pretty obvious. They're like simple enough arguments that they're obvious, right? Like disjunctive syllogism. If it's P or Q, but it's not P, then it's got to be Q, right? Addition. Hey, if P is true, then P or Q is also true. And simplification. If P and Q together as a conjunction is true, then individually P is true. Or alternatively, individually Q is true. This over here could easily be a Q if you wanted instead. You can also sort of flip side of simplification. You can also just combine things together. If you know P is true and you know Q is true, then you know P and Q as a combined conjunction is also true. Okay. Resolution is a little harder. Resolution is one of the harder ones to understand. It's a little weird. It's sort of like P and Q, P or Q and not P or Q. Remember that either P or not Q has to be true because we have the law of the excluded middle, right? Like a proposition can't be neither true nor false. It has to be one or the other, not both, right? It's an XOR scenario. So if you've got to have P or not P, then that means that either you've got to have Q or R, which is resolution. So that's a little harder to wrap your head around. I don't want to spend a ton of time talking about it. So those are the ones we can use for now. Now, right here in your table, it kind of switches from talking about propositional logic up here. This is all propositional. Sorry, it's the reason I don't do this very much. Propositional, I can't write propositional. Anyway, I'll just say it. Down here, these rules of inference are useful only with predicates and quantifiers. As you can see here, they're using for alls and there exists and that kind of thing. So we'll get back to that. So we want to have this handy on the side somewhere. So let's kind of stick it there and then have this over here. So what we want to do is we want to try to, in order to prove the validity of this more complicated argument, we're basically going to use the simple arguments called rules of inference, and we're going to string them together to make a sequence of arguments that leads us from these premises to this conclusion, right? So we are chaining together simple arguments to produce a larger argument. And since we know that the simple arguments are all valid, we can therefore prove the validity of the larger argument. Does that make sense? Let's see what it looks like. So one of the first things we can do here is to look at 1 and 4, premises 1 and 4. We have P or F, but also not F. That matches one of our rules of inference over here. Can anyone see which one it matches?
The hypothetical one.
Hypothetical syllogism?
Wrong one, sorry. No, the one above it.
The one above it? Modus tollens?
Oh, below it, it's disjunctive syllogism.
Disjunctive
You're right,
syllogism?
You're right. I don't know where my brain is right now, so it's fine.
That's okay, John. No worries. Looking through here, yeah, we've got the P or F. So we have an or statement, and then we have a not F. Yeah, that's a disjunctive syllogism scenario, isn't it? We have, it's very similar to this, but with, I guess it's using F instead of Q. And instead of having not P, this is like not the second one, but we know that or is commutative, so it doesn't really matter which of the two you have not of, right? So like, this is a disjunctive syllogism setup here. So what we can do is we can start our proof of validity by making a conclusion based on that rule of inference. Okay. Actually, I guess technically the first thing you do in your proof is you assume premises 1 through 4 are true. And writing the words are true is kind of optional here. If you just say assume premises 1 through 4, it's implied that what you mean by that is assume that they're true. Like when you say assume something, it means assume it's true. Does that make sense? So you don't really have to say are true. You can just say assume premises 1 through 4, period. And it's implied that you mean like assume they're true. So that's the first thing we do. And then we can say, aha, the next thing we can do is write that P must be true by disjunctive syllogism with 1 and 4. And this, every time we assert a new statement, the truth of a new thing, we're going to label it with a number. The type of proof we're writing right here is a very strict structure proof, where every line is numbered, and we can refer back to previous statements in our proof by just referring to them by their number. This is a very strict format for a proof. Not all proofs are strict like this, but when you're doing this type of proof, proving an argument using rules of inference, I do want you to do it in this strict format. Say we have premises 1 through 4, and then we can state 5. P, it must be true because we had P or F, but not F. And that is a disjunctive syllogism. So now we can use 5 in the next few things. So now we can look for whatever is next. What can we conclude next? Get rid of my circles here; those don't need to be there. So looking through the other premises, is there anything else we can do, especially now that we know that P is true? A couple different directions we can go here. often you'll find there's more than one possible way to do this. And so in this case, one thing we can do is to say, well, if we know P is true, then we know not P is true. That's not a rule of inference, but it is a propositional equivalence. It's the double negation propositional equivalence. And when you're doing a proof like this, these propositional equivalences are also available. They're not arguments, so they can't really give you a new statement, but what they can do is just rewrite an existing statement you already have in a different format, which might make it compatible with one of the other rules. Kyler, question?
Could we technically infer T is true as with line 2?
Just from line 2?
Well, with the fact that we have proven P, can we not also infer that T has to be true if it cannot be false?
You can. What rule of inference is that? Or
I don't know if it's considered a rule of inference, but immediately it must be modus tollens is the most likely culprit, but that even doesn't make sense.
modus tollens says if P implies Q and you know not Q, so if you know that if you know that the conclusion of an implication is false, then you also know that the premise, the hypothesis is false.
Then is it modus tollens?
It's very nearly modus tollens. Let's see. So I was leading us towards modus tollens here as well. So I said we can say not P. That's just double negation, double negative there. With 5, right? Double negative of 5. But then this is the negation of the conclusion of number 2, right? So we have a double. This is a little messy with double negatives. We have a double negative here. It's like we have not Q, because the Q is this, not P, and so not with that would be not P. And so then we can conclude by modus tollens here, we can conclude the negation of the original hypothesis, which in our example here, the hypothesis was not T. So what we conclude is not T. That is modus tollens using 2 and 6.
And that brings up a whole different question of how does that interact with vacuous truth? How are we confirming that T is P, T is true if P is true when that is not always the case?
So the thing with modus tollens is like this. If you know that P implies Q, and I'm just going to use the letters over here for now. If you know that P implies Q is true, but you know that Q is false, then if you think about the truth table for an implication, let's write that real quick. Okay, so here's the truth table for P implies Q, right? If you know that P implies Q is true, right? If that's one of the premises in your argument, then that means that you are in one of these 3 cases. Okay, you're in one of those 3 cases. You're not in this one. But if you also know that the conclusion is false, Q is false, then that is right here, which narrows you down to this case only, and that rules out that one and that one. And so now you can conclude that the premise P must also be false, because that's the only line in the truth table left. So this is modus tollens right here. It actually, again, relies on vacuous truth, right? Because it's saying, well, if P implies Q, but Q is false, then the P implies Q must be true vacuously. So P must be false. It can't be true any other way. It can't be true in the regular way. It's got to be one of those vacuous truth cases, that one in particular. Yeah. So yeah, this is modus tollens really leans heavily on vacuous truth. A lot of these lean heavily on vacuous truth. So yeah, so that's the next step here is we say, all right, well, that means that not T is actually true. There was an alternative step 6 and 7 that I want to propose here, which might make a little more sense because dealing with double negatives can be kind of annoying. So what you could do instead is take your not T implies not P from the original premise 2, and you can rewrite that using the contrapositive equivalence. The contrapositive of not T implies not P is just P implies T, like that. Just P implies T. And so then that's, I'll just write contrapositive there. Contrapositive of 2. Okay. So then that can be combined with knowing P. If P and P implies T, then you can get T directly by modus ponens this time, using 5 and 6. Okay, so this is an alternative approach to the same thing, right? It's almost like modus tollens and modus ponens are the same idea. It's just that if you kind of combine modus ponens with contrapositive, you get modus tollens. So that's what I'm doing on those lines there. So I'll call that 8 as well, because it was 8 over there. Now, once you've got T, you can get B using premise 3. T implies B, right? You've got T, now we can say B. That's a modus ponens as well, using 3 and 8. And then that is what you were looking for. So we strung together all these rules of inference and ended up arriving at the conclusion we were looking for. And so this then proves the entire argument, the entire big argument is valid by leaning on the smaller arguments, which we know are valid. So we can say, therefore, the argument is valid. QED. Cool. Okay, this page is getting a bit messy, so I'm going to export it. Let's do another one. So this one's going to look familiar. I'm getting this. I had these written up in Microsoft Word, so that's why you can see the little grammatical. Thinks that I should have made a grammatical correction there, but it's wrong. Anyway, don't worry about those little blue lines. This is familiar. This is the one I presented. This is the argument I presented just a few days ago when we very first started talking about like predicates and quantifiers. All birds native to North America can fly. Turkeys are birds. Turkeys are native to North America. Therefore, turkeys can fly. So let's see how we can represent this. Here are the predicates we want to use. So let's go ahead and represent this. We can say for all, well, first of all, let's state that our domain is going to be like all things. We'll use a very broad domain here. All things. So in the first premise here, we want to say for all things, if they are both a bird and native to North America, then they can fly. So we have to include the B of X and N of X in our hypothesis there. Then they can fly, F of X, like that. So that's our first premise. Our second premise, turkeys are birds. So I'm going to say B of turkeys. I'll just say B of turkey, or I might abbreviate that as Turk as I get going here. And then turkeys are native to North America. That's just N of turkey. So I'll write N of Turk. And then therefore, turkeys can fly, F of Turk. Okay. So let's write a proof of the validity of this argument. Our premises we'll number 1, 2, 3, and we can refer back to them by number as we write our proof. Now, it may be, there's a few different things we need to do here. It may feel, this is tricky because it may feel like the conclusion is already obvious and you don't need to do anything. But that's not true. We need to be careful. We need to be rigorous. And for that, we need to break things down into small steps. So one of the things you might want to do that might not seem obvious is to use the conjunction rule to combine B of turkey and N of turkey. So the reason for that is because this implication up here that we're going to want to lean on eventually, its hypothesis is B of X and N of X. And so we need to conjoin the B and the N together in order to have the correct hypothesis for that implication. So that's the very first thing I want to do here is use conjunction. We know P is true and we know Q is true, so we're going to conclude P and Q. So I'll just write for
Can you use, can you use capital F as a variable, even though it's like false as well?
Oh, you're right. It is a little bit annoying to use capital F as a function. Would you rather I use a different letter? I think maybe that would be a good idea.
Yeah.
Let's use something other than capital F. That's a good idea. Thank you for. What was that?
Y, maybe.
I'm okay with Y. You guys okay with Y? For flying?
That works.
Sure. Sounds good. Thank you for pointing that out. That was a bit of a bad choice on my part. Okay, so Y of X and Y of turkey. So now we have B of turkey and N of turkey. That's just conjunction. So we can abbreviate that conjunction of 2 and 3. Now the other thing is to look at the fact that number one, we're gonna want to basically use a modus ponens here, right? Like we're kind of leading towards saying modus ponens because we've got the hypothesis and we want to get their conclusion. But the other issue is that this is a very specific statement about turkeys, whereas this is a specific statement about all things. I'm sorry. It's a general statement about all things. The problem is that it's not specific yet. But since this is being claimed to be true for all things, X, we could specifically say that it is true for turkeys. But that in and of itself is a rule of inference. So looking down at the last 4 rules of inference, these ones are instantiations and generalizations. And these rules of inference are actually, they're sort of like bridges between predicate logic and propositional logic. And so what we need to do is take this quantified statement with predicates, and we need to instantiate it, which means apply it to a specific instance of the variable. So we're going to use the universal instantiation, which says, this one here that says, if you know for all x p of x, then you can say p of c for any particular c, whereas c stands for like constant. It's just a particular value of that variable can hold. So over here, I can instantiate number 1 with x equals turkeys. So I can say b of turkey and n of turkeys implies y of turkeys, right? That's a universal instantiation of 1. Only then, after I've instantiated that, can I now apply my modus ponens that I want to obtain y of turkeys. Modus ponens of 4 and 5. Okay. Oh, and we are almost out of time. I didn't quite get to my final one. I'll put it up on the board. You guys can think about it over the weekend, and then we can maybe go over it first thing on Monday. So I prepared this one. I like this one. I prepared this because it uses more than one. It's an example of an argument that uses multiple variables. All right. So Tristan is an island. Did you know that? Tristan is an island. Here, I'll show you. This is Tristan da Cunha. It is famous for being the most remote island in the world. It's in the South Atlantic Ocean. It's like a 6-day boat ride from South Africa. You can only get there by boat because it doesn't have an airstrip. So Tristan da Cunha is an island. Vera is a person who lives on Tristan. Let me introduce you to Vera. Here is the island council. This here, this lady in the front, that's Vera. Vera lives on Tristan da Cunha. And then we'll say this: if there is a person living on an island, then the island is inhabited. Now that's a very general statement. If there is a person living on an island, then the island is inhabited. But with that very general statement, we can specifically conclude, given the information we have about Tristan and about Vera, that Tristan is inhabited. So we're going to have to, for that one, we're going to have to work with these instantiations and generalizations, these kind of, last four rules of inference down here. We're going to have to kind of work carefully with those in order to use this very general statement to arrive at this very specific conclusion. Okay, so that's where I'll leave it for today. I hope you guys are feeling okay about this. Like I said, next week we're going to do proofs. We're going to kind of broaden our study of proofs to be a little less strict. Like so far, we've had a couple different types of proofs. We've been proving propositional equivalences, and we're proving validity of arguments. The types of proofs we're doing so far are these very strict formats, right? Where we line by line cite our justification for everything very carefully. And that degree of rigor is to some extent going to carry over into our proof writing that we work on next week. But we are going to loosen up a little bit and start writing our proofs a little bit more casually. And we're going to do it, start doing it with like complete sentences and paragraph format and that kind of thing. So get ready for that. Okay, we can't loosen up entirely. There's some elements of the step-by-step rigor and citing justification. There's some elements of that rigor that we do need to keep. Okay, because we can't completely throw the rigor out the window. Proofs still need to be rigorous, but it's just that there are more casual ways of writing proofs that are conventional, and I want to try to teach you those conventions. All right, that's all I want to say. So have a great weekend, everybody. See you Monday.
Have a great weekend.